Hello, this is Dr. Liu. In this second video, we have another question, which is also a circular shape. So we have a solid sphere with a radius 0.1 meters and mass 0.26 kilograms. It rolls down incline plane without slipping. If the incline plane is 0.5 meters tall and it has an angle of 30 degrees, then how long does it take the sphere to roll down the incline plane? Okay, so this problem would require some rotational dynamics because the time was asked. How long, right? So let me create a diagram first. We'll give some space to the derivation. Approximately 30-degree angle. Sphere. Okay. So it rolls down without slipping, and that would correspond to the same non-slip condition, right? So we'll have that somewhere. Let's put the numbers in. We have a radius, so r equals 0.14. We also have mass 0.26. Oops. Okay, and we have 0.5 meters, so it's that 0.5, and then we also have the 30-degree angle. Then we have this formula. This is a formula for solid sphere, how much rotational inertia it has, and we would need to do that calculation, but not at this moment. So we're given a lot of these parameters. The way to find out time is to find acceleration, right? If you know the acceleration and you know how far this sphere has to roll down, then you can use kinematics to find out one-dimensional kinematics. So we'll focus on finding the acceleration. But since it's a rotation problem, we'll probably first find the angular acceleration, or somehow convert this into linear acceleration in order to find it. So let's zoom in to the sphere. Let me draw a bigger sphere on the right side. And we'll have this inclined plane. Okay, so the center of mass is right here. This is where the sphere is in contact with the inclined plane. So force-wise, the inclined plane has normal force. Okay. Maybe move that center of mass. Okay, so we have a normal force from the inclined plane. We also have friction. Without friction, the sphere would not roll. It would just slide down, right? Think about a very slippery incline. Anything will just slide down without rolling much. So there will have to be a force friction that holds this point of contact instantaneously at rest. Although the point of contact would like to slide down like that. So that tells you the force of friction should point upward to prevent that sliding down. And this is a static friction, so there's no loss of mechanical energy. So the friction pulls up, normal force pushes away, and here we also have this gravity here. Let's draw a slightly shorter line. Okay, so gravity pulls down directly from center of mass. All right. And to analyze the rotation, let's first pick an axis of rotation. So axis of rotation, the choice would be, well, you can pick here, the point of contact, center of mass, anywhere else. But the benefit of picking one place against another is you'll have less unknown forces or unknown torques. So if you picked here, gravity will have zero torque. It's a known force, but that's okay. Normal force will tend to go through this point, so normal force also has no torque. It is an unknown force with unknown torque. Now it's zero. That's good. But friction is also unknown. And if you pick the axis rotation here, then friction will have a lever arm, the length of the radius. So we'll have to deal with friction's torque. which is not very easy. So we'll pick the axis of rotation right here at this instantaneous stationary point. So this point, that is where the sphere is in contact with the inclined plane, it is not moving. We call this instant center of rotation. So we usually pick that point to be where our axis of rotation is. So now we pick this point. These two forces are coming out of that point, so they will have zero torque. So let's say axis of rotation at, I didn't really have a name for it, so I call this center C. Maybe I can call that A, point A. This is point C for center. At point A, so the lever arm of normal force is 0, and the lever arm of static friction is also 0, but the lever arm of gravity is not 0. So gravity is here. The perpendicular distance between gravity and the axis of rotation is a horizontal line that looks like this. It's a bit too low. It looks like this. So this line is, let's use a different color. So this is lever arm of gravity. And we can extend this a little bit just to see that this angle is the same angle as this angle, the angle of the incline. Just think about this fact that if you decrease the incline's angle like this, and this line will be more vertical, right? Will get more vertical, and this line doesn't change. That means the angle between them will just start to close down to a smaller angle if you lower the inclined plane. You could do a bit more rigorous proving, but this is the inclined plane's angle. Inclined plane's angle is the incline with horizontal, and this angle is the normal of the incline with the vertical. So you could prove it if you want. So okay, this length here, the physical length, that's the radius of the sphere, and that's the angle theta. This is perpendicular distance. So in this right angle triangle, we have that distance is r, the hypotenuse times sine theta. Okay, so we found this is r sine theta. Alright, so that's the torque. And since there's no other forces having torque, this is the only one with torque. So let's go back to black marker. So torque is equal to just the torque of, let's put net, torque of gravity. And think about the direction of the torque. This is rolling down like that, right? So the rotation, if you follow this rotation with your right hand, with all your four fingers or thumb points out of the screen, so that is a positive torque. So this torque, which is equal to the force times the lever arm, is equal to mass gravity times the lever arms r sine theta. Okay, so now we have torque. The torque is equal to rotational inertia times angular acceleration. Okay, so since we have axis rotation here, the rotational inertia should be calculated around here. Just think about the sphere is rotating around this point, not the center. So this rotational inertia is around A instead of C, the center of mass. The way to calculate this rotational inertia is to have the rotational inertia around the C, which is that, plus total mass, how far they're apart, r, and squared. So this quantity is 2/5 mr squared, as in the hint. And here we also have another mr squared because we're not rotating around the center. So that becomes 7/5 mr squared. Okay, so we have this. We have the whole left side. We'll be able to get the angular acceleration. So let's plug this into that. So we have mgr sine theta equals 7 over 5 mr squared alpha. And because the rotation without slipping condition, we can have v equals omega r, and at the same time we can have a, the acceleration of the center mass, is equal to alpha r, angular acceleration times the radius. So now we can replace that with alpha equals a over r. So this right side is 7 over 5 m r squared a over r, or if you divide out that r, 7 over 5 mr times a, and the left side is this. So mgr sine theta. We can divide out m, we divide out r, so m and r are gone, and we have g sine theta left. 7 over 5. Let's see, m and r are gone, so we're only left with a. So that gives us the acceleration. A is equal to 5 over 7g sine theta. I don't really know if you recall this, but without the consideration of rotation, if there's just a block sliding down without any friction, the acceleration is actually g sine theta, depending on the angle of the inclined plane. Now we have a fraction. We have a number that's slightly smaller than that, which means it's going to accelerate to a slightly smaller center of mass speed, because of the rotation also stores some energy. It would require some energy to do. So now we have the acceleration. We can calculate how much time it takes to accelerate all the way down to the bottom, and this will be the distance traveled. So let's call this distance L. Let's just write right up. Okay, L. We have the height, we have the angle, so we can find out this L here, length is 0.5 divided by sine 30 degrees. Okay, that's because this is opposite to the angle, right? Opposite over hypotenuse, that is sine 30. So then opposite over sine 30 will be hypotenuse. And sine 30 is a half. So half over half is a 1 meter long along the inclined plane. So let's put a unit here. Okay, so we can use this formula, the 1D kinematics. We have x equals x0 plus v0t plus 1/2 at squared. Assuming that x0 is a 0 and x is equal to 1, we end up all the way down the inclined plane. And v0 is 0, it was starting from rest. And we know the acceleration. Oh, I didn't really calculate this into a numerical value. So let's use okay, Python. So 5 over 7 times 9.8 and then times sine 30, which is 0.5. So we have 3.5. meters per second squared. Okay, 3.5. And what else do we have as parameters? We have t. We don't really know t. We also don't have final v, which we don't really care how fast the sphere's center mass is. We just want to know how long it takes. Right? Okay, so let's plug all this into that formula. So 1 meter is equal to 0 plus 0t plus 1/2 3.5 t squared. So we have 1 is equal to 3.5 over 2. I think 1.75. 3.5, 1 3/4. Yep. So that's the time. So t is equal to 1 over 1.75 square root. Let's use our calculator. 0.57, okay, 0.571 square root 1756 seconds. Okay, so this question is relatively difficult because it requires us to analyze torques, and also it requires some additional knowledge of where to pick the axis of rotation right here with the instantaneous point that is at rest, right? The sphere does not slip, so the sphere's contact with the inclined plane is instantaneously at rest. And then it also requires us to find the rotational inertia that is not exactly through the center of mass, but through where it's rotating. Okay. So with all that together, our goal was to find the acceleration or angular acceleration, and with that acceleration found out, we can use 1D kinematics. So we start from rest and we go a whole length of the inclined plane to find out how much time it takes to get there. Thanks.